Okay, last time we left off with sampling distributions, and now I'm going to go through what we call the three amazing facts. Okay, in the smoking study, we did this, uh, uh, we selected a ton of samples, calculated the mean, and then plotted the relative frequencies of those means. So we plotted the proportion or the relative frequency of the means selected from all the possible random samples. Or we would do this an infinite number of times where we selected a random sample, calculated the mean, then we recorded the mean, then we plotted the relative frequency of the mean. Okay, this is a sampling distribution. Now notice we took a distribution with a positive skew and unimodal, asymmetric, and turn that into a sampling distribution, which looks pretty normal. It turns out that if we were to take a rectangular distribution of scores, construct a sampling distribution of sample means, we would wind up with a normal distribution. If we took some sort of bimodal distribution, right, of scores, translated that, constructed a sampling distribution of sample means from this underlying distribution, we would wind up with a sampling distribution that has this shape. This leads us to the following conclusions, or the following what we call three amazing facts, and they come from probability theory, from Domov, from Bernoulli, and from others. The first is that the mean of the sampling distribution of the sample mean is equal to the population mean. This notation right here, mu sub m, is the mean of the sampling distribution of the sample mean, and that's equal to the population mean. It turns out that the standard deviation of the sampling distribution of the sample mean is equal to the standard deviation of the population divided by the square root of n. You can see that here, is that this is another amazing fact of sampling distributions of the sample mean. And the last thing, which is probably the most amazing one, is that as the sample size increases, the sampling distribution of the sample mean approaches a normal distribution. It's what we call the central limit theorem. It's together these three things that we call the three amazing facts of probability or of sampling distributions of the sample mean. Memorize these. These become really important. Okay, all sampling distributions are probability distributions, but not all probability distributions are sampling distributions. The probability distribution of scores is what a sampling distribution is constructed from. So they're related, but they're not the same. Okay, and you got to keep these separate. A probability distribution is just a distribution, the possibilities of a score. Sampling distribution is the probability or the possibility of a statistic. So it's all the possible levels of a sample statistic and their probabilities. And we're going to be interested in studying statistics. So we want to be able to make predictions about what we think a statistic is going to be, or where it's going to be, around what value it's going to have. The central limit theorem, if you think about it after a while, blows you away. As the sample size increases, the sampling distribution of the sample mean will approach a normal distribution. And what I tried to demonstrate in the previous couple slides is that the shape of the distribution of scores, that is the probability distribution of scores, does not matter. The sampling distribution of the sample mean will approach normality no matter what. As the sample size increases, the sampling distribution will approach a normal distribution, and that's pretty awesome. And actually, that's pretty amazing. And it's an amazing fact because of theorems like Domov's theorem and Bernoulli's theorem and probability theory. With large enough sample sizes and the sampling distribution approaching normality, the probability of certain results, certain statistics, can be found using z-score transformations in Table A. For example, a psychology class with 25 students had a mean SAT verbal score of 535. What is the probability of having a class of this size with a mean SAT verbal of 535 or higher? Well, we know that the population mean is 500, the population standard deviation is 100. We know that the mean of the sampling distribution is equal to the mean of the population, and the standard deviation of the sampling distribution of the sample mean will equal the standard deviation of the population divided by the square root of n. We also call this term, remember, sigma sub m. We call it the standard error of the mean. And that's why it's related, and that's why we use the m. It is related to this sampling distribution of the sample mean. If I do a z transformation here, where sigma sub m, or the standard error of the mean, is just the standard deviation divided by the square root of n, I wind up with a z-score of plus 1.75. A z of 1.75 is a proportion of 0.9599 of the scores below it. Okay, that means that there's a 4.01 chance of getting a mean of 535 or higher. And that's a pretty low chance. So this is probably overall a pretty smart group if we're talking about a particular class and their mean SAT verbal scores. Okay, random sampling, just to review, a process by which every observation has an equal chance of being included. 3 amazing facts of sampling distributions are that the mean of the sampling distribution is equal to the population mean, that the standard error of the mean is equal to the standard deviation of the population divided by the square root of n, and the central limit theorem, and that is the shape of the probability distribution of scores does not matter. As n increases, the sampling distribution of the sample mean will be normal. And once we have a normal distribution, we can use a z-score and table A to find the probability of some particular mean or statistic that's normally distributed. All right, now we're going to get to the real stuff of